All right, can everyone hear me? Good. So, my name is Alexis King. I'm going to be talking about a programming language that I've been working on. It's getting near the end of the first day of Kurion, which is exciting, so I'm sure everyone's brains are a little bit full at this point. Mine is as well, but I'm going to try and shove a little bit more in there before the closing keynote. So I've been working on this programming language for a little while now, about 1.5 years, just mostly in my free time. It's very much still a work in progress. I would not recommend you go home after this talk and rewrite all your software in my programming language. But it's gotten to a point where I can show it off, and it has some cool things. So as you can probably infer from the title of this talk, the name of the programming language is Hackett. And I like to start there because the name is actually meaningful, and it sort of hints at what the programming language is. So specifically, a little bit about myself. I'm currently employed as a programming language researcher, and that means that I really, really like programming languages. But even though I've used dozens of different programming languages, there are two that really stuck with me for a very long time. And even though I'm currently employed as a researcher, that actually is only the case as of about 2 or 3 months ago. Before that, I was working as a software engineer writing Haskell. And Haskell is a wonderful language. It's a pure statically typed functional programming language. You've probably heard all the buzzwords by now. But it's a really, really wonderful programming language. The other language that I found myself really gravitated to was Racket. Now, Racket is a completely different kind of language. It's a Lisp descendant. It's a Scheme descendant. But I think just describing it as that really sells it short. I could probably give 3 talks and not cover all of the content in Racket. But I think that the thing that really stands out is its really powerful macro system. It's sort of unparalleled in that respect. There isn't really one best type system, right? It's sort of orthogonal. But as macro systems go, there are very few competitors to Rackets. So I really, really like both these languages. And I said, why should I have to choose just one? I want to have both at the same time in one language. And so that's where Hackett came from. Now, if you're not familiar with either of these 2 languages, or you're not intimately familiar with both, this probably doesn't mean all that much to you, and that's OK. I'm going to explain, first of all, why you should care about both of these languages, but also I'm going to rephrase sort of the ideas, reframe the ideas in sort of 2 big points of the language. The first one is that I really like Haskell. I like the way it works, but I want the language to be extensible. And a good way to do that is to use a macro system. So I think that not only do I want to use macros in Haskell, I find that there's actually active requests from the community to have macros in Haskell. They just don't know that that's what they're asking for. So I'm going to give a couple examples of that later. But then sort of the more subtle, more interesting point is that I actually think that I can write more expressive macros if I have access to a type system like Haskell. And this is sort of subtle, because a lot of the time people don't really think of these 2 things as benefiting one another or working together. They're sort of orthogonal. But I'm actually going to make the claim that I can have better macros with a type system like Haskell's. And I'll get to that a little bit later in the talk. But first, I just want to actually show what the language looks like so that you get a feel for what it is and what it's like to actually run programs. So this is Dr. Racket. If you've written any Rackets, you've probably seen it before. But essentially, it's just an IDE. It's just an editor. And this is a small Hackett program. Now, this is a Hackett program specifically that implements a web server. It's not a very interesting program, but I can run the program, and it says it's running the server on port 8080. I can go over to my web browser, and I can go to 8080, and it'll give me not found, which is great. And I can say, hello, Curry on 2018, and it says that. But it can do a couple of other minor things, too. So it can add numbers together. So I can say add 3, 2, 5, and it'll give me back 8. And if I give it some nonsense thing that's not a number, like hello, it'll complain. And it can also calculate the distance between 2 points. So I can say distance from 1, 1 to 2, 4, and it gives me back some long floating point number. So of course, this isn't very interesting. This isn't a very interesting program. But it is interesting to look at how it's implemented for a couple of reasons. First of all, it doesn't look very much like Haskell. It has all these parentheses in it. But it is statically typed. So for example, if I go down here and I change this 8080 to a string, then it will complain. And it will say, if you can see down at the bottom here, it says, oh, it went away, type mismatch between string and integer, and it highlights the offending part of the program. Oh, yeah? Move it up a little bit. Oh. just hold it. Yeah. All right. Is that any better? Maybe? Hello? All right. Let me know if that's a problem. So anyway, so it's a statically typed programming language, so it highlights the offending part of the program in red. And additionally, if I change the program to be type correct, and I hover over parts of the program, then it actually gives me nice type tooltip. So you can see this is it's probably really small from there, but this is a function from integer to IO unit, as well as if I hover over other parts of the program, it gives me type tooltips. So the other thing that's really interesting about this program is this blob right here. I can make the code a little bit bigger. This def server thing. And this is a little DSL. It's specifically a macro that implements a web server. So I can basically specify in a declarative way that I want, if you make a GET request to hello, and then you give it a string, it'll give you back a string, and it calls this greet function, which is just an ordinary function on strings in Haskell, or in Hackett. And same thing with add and distance from. And distance from even computes something on a data type that I define in this module, which is defined right here. It's just an algebraic data type. In order to know how to convert back and forth between say URL, fragments of a URL, and my data type, I just define a little type class instance. So if you're not familiar with Haskell, not all that necessarily means anything to you, but that's OK. It's probably understand the gist of it. So the most obvious thing about this program is that Hackett is a Haskell. So fundamentally, again, it probably doesn't look all that much like a Haskell, but if we put sections of Hackett side by side with Haskell programs, it looks almost identical. Here's an algebraic data type definition in Hackett, one in Haskell. You can see really the only difference is that we put some more parentheses in there. The same thing is true of, say, pattern matching, and there's some infix operators with applicative notation. Again, if you're a Haskell programmer, that probably means something. And same thing with, say, do notation and type class instances, right? So we can do kind of the same things that we do in Haskell in Hackett. So Hackett is a Haskell, but of course that's not the whole story. If it were the whole story, this would be a very boring talk, and I would say done and give me any questions. But that's not the whole story. So the interesting thing about this program is this sort of def server thing, which I pointed out earlier. And again, this is a macro. So what is a macro for those unfamiliar? If you're familiar with list macros, you probably know all of this already. But essentially, the idea of a macro is that we can take some program, some new thing that we want to add to our programming language that might not currently exist in our programming language, and we can define it in terms of a translation into simpler features of the programming language. So in this case, this def server thing just gets translated into function calls and pattern matching and ordinary things that you would find in Haskell and in Hackett. And obviously, it's a lot more code, but it's simpler code. It's made out of simpler constructs. The advantage of doing this, of course, is that we can make the code a lot easier to understand, a lot smaller, a lot easier to read, and we don't have to worry about all the stuff that it generates. But it is a nice abstraction, and we're able to do that. And of course, we can't implement this sort of thing as a function because it generates a new definition, does things like that, which can't be implemented using other abstraction tools in our programming language. So how does this actually work? Well, a macro is defined as a function from code to code, just sort of what I was saying. We take some code and we produce some new code. And specifically, the key point here is that they're defined at compile time. So the compiler walks the program as it's compiling it. It finds all the uses of macros. It runs the function. It replaces them with the expanded version of the macro. And then eventually, it ships the fully expanded program off to the compiler. It gets compiled using a traditional compilation toolchain. So that's great. So macros are syntactic abstractions. They let us build these abstractions that allow us to change code. It's a metaprogramming tool. But they allow us to build DSLs. So that's one example of what macros can do. But they can do a lot of other things, too. It's not just building DSLs like this. So I actually found a couple of examples of this. You don't need to read this. The text is very small, I know. But you can take my word for it that it's from a post to the Haskell subreddit, where somebody is complaining, I've got all this code that's really repetitive. And I've translated it into Hackett notation. But this is essentially what they were complaining about. And they say, I've got all this repetition, but I can't abstract over it because the thing that I'm abstracting over is a pattern. And in Haskell, patterns aren't first class. So you say, oh, well, maybe we translate all this code to use lenses. Those are kind of like first class patterns. And then we can pass those to a function. But with macros, we don't have to do that because we can just abstract over the code pattern directly. And indeed, we can write a really simple notation that's fit for purpose. And if you use this notation all over your code base, that's a big readability one. It's a big maintainability one. If you change what sort of that pattern does later. You don't have to change every single use site. You just change the definition of the macro. And you might say, well, that seems like a lot of effort to build a little language just for some random thing that I came across when building my program. But it's really not, because this is the whole macro. It's less than 10 lines of code. Now, I'm not going to get into the details of how the sort of Hackett system for building these macros works. I'm not going to explain every line of code here. But basically, if you were interested in writing macros, there's information that would help you learn about this, and then you could write these really simple fit-for-purpose macros. Another example is this one. So this is sort of two mutually recursive functions that I found in a blog post from a little less than a year ago. The two mutually recursive functions take a Boolean as an argument, and if you actually read through all this code, you don't have to, because I've done it for you. It's actually only used right there. That's the only case where the Boolean value is scrutinized. But because these two functions are mutually recursive, it has to be threaded through everywhere. And so somebody said, wouldn't it be great if we added a new feature to Haskell called the section thing, where we can say, well, in this section, all of the functions that I define will implicitly have another parameter. And outside of the section, you'll explicitly provide the parameter. But inside of it, we don't have to worry about threading it all around. So normally, this would mean, OK, we have to make a change to the compiler. We have to go through the GHC proposal process to say, is this something that we actually want to add? But somebody pointed out in the discussion that you can actually define this in terms of existing features in Haskell. And the commenter, or the author of the blog post, responded to this saying, if only we could get rid of the boilerplate in the first 3 lines. Of course, macros allow you to do this. So this is a little bit of a disclaimer. This macro wouldn't work exactly as written in the existing implementation of Hackett. None of the reasons for that are fundamental. I just haven't implemented one of these things. So, but essentially, you could do this, and it would work. So macros are syntactic abstractions. They give us better DSLs. They help us to eliminate boilerplate. They let us extend the language with new features without having to modify the compiler itself. We can experiment with those features. We can find out if they work or if they don't. Haskell programmers want to be able to do these sort of things. And Hackett gives that to them. So this is the simple proposition of Hackett. This is sort of the first order idea of what Hackett is. And it already is able to do some of those things. So clearly, I think, hopefully I've convinced you that Haskell can benefit from macros. But of course, the people who are Lisp programmers are going to say, what can Haskell do for me? And I'm going to tell you that it can do a lot. And it's not just the things that you might be thinking that I'm going to say, which is that I can give you static verification, I can give you program correctness. Those things are nice. But I'm going to essentially make the claim that Haskell is able to make a macro system better at metaprogramming. How is that? Well, here's the thing. The title of my talk is a little bit of a lie, because I claimed that I was going to present a metaprogrammable Haskell. But Haskell is actually already really good at metaprogramming. So just look at some of the libraries on Hackage, the Haskell package system. There's DSLs for all sorts of different things, for parsing, for handling command line arguments, for producing HTML. This is the one, though, that I think really sold me on Haskell when I first saw it, before I became a Haskell programmer. This is similar to what I was talking about at the beginning of my talk. It's a DSL for building web services, RESTful web servers. So here's all you have to do. In Haskell, you write down the API of your server as a type. You write a type-level thing that describes your API. You write a couple of really small functions from your data types to your data types. You don't worry about serialization. And then you write like a 3-line function that says serve this API. And that generates a web server for you. And that's amazing. That's clearly some kind of code generation. Some kind of metaprogramming is happening here. But there's no macros involved. How is that possible? And the answer to that is type classes. So a lot of languages have type class-like things. I don't think there's any programming language in existence that has precisely the set of features that Haskell's implementation of type classes has. And while type classes are not normally used for metaprogramming, they can be in much the same way that C++ templates are used for metaprogramming. So with type classes, ostensibly, the original idea was that we want to have a principled way to overload things, right? So if I want to have, so normally you can have function overloading in a lot of languages. In Haskell, you can also have value overloading. So you can say, if I want an empty list of integers, it gives me the empty list. If I want an empty optional, which is like a maybe integer, then it gives me back nothing, which is like none in some other programming languages. But the interesting thing here is this means that the program's behavior depends on its type, which is different from a lot of programming languages, right? We take the expression, we make sure that the types are correct, and then we throw the types away, and we evaluate the program. And that's kind of disappointing to me because it seems like I'm paying a lot to get, I mean, not having bugs is cool, yeah, but it's not exciting, right? And of course, it doesn't catch all bugs, as the people who don't like static types would be quick to tell me. So this means that in Haskell, when we evaluate a program and we don't know what its type is, we don't actually necessarily know what it's going to do. We need to have the types. So how is it that when we add a type annotation, we suddenly know what the meaning of this program is, despite the fact that the types go away at runtime? Haskell performs type erasure. When it compiles the program, it checks the types and throws all the types away. Well, the answer is that there's actually a compile time transformation that converts a program with types to a program essentially without types. I'm simplifying things a little bit. But it actually performs a compile time transformation and produces a program that you can evaluate without the types having to stick around. And this is fascinating, because this means that we now have compile time functions from types to expressions, from types to code, similar to the way that we had macros, which were functions from code to code. It's a little different, but both techniques allow us to perform code generation. So this means in many situations, this doesn't seem very exciting, because if we just provide the type annotation, it doesn't seem like it gets us very much. But of course, Haskell has type inference, which means that most of the time the types can be inferred. So implicitly, even though we never said how we should translate this program, the compiler can figure out, OK, because you're using this as a list, I will perform the list transformation. And this is fascinating, because now Haskell has these two worlds, expressions and types. And we can use type inference to go from expressions to types. And then we can use type classes to go from types to expressions. And we get an interesting feedback loop here, where we can actually start performing code generation just by using these two language features. Hopefully that makes sense. I'm going to give a couple of examples. So first of all, the servant example I talked about earlier, it's this serve function down here is a type class constrained function, and it uses that type level thing to then actually generate code. Now, admittedly, this isn't an ideal DSL, right? Because that type level thing is kind of difficult to understand. Indeed, there's a steep learning curve. But it's using type classes to perform the code generation, also to associate information about how can we serialize these things and deserialize these things. So that's all very useful, and it's being propagated by the type system. So let's do a side-by-side comparison of macro metaprogramming and type class metaprogramming. So when we have a macro, just some macro, let's call it mac, and it's applied to some expression, then it might expand in some big thing. But importantly, the expression that's passed to it essentially has to be treated like a black box, right? It can't know anything about what's inside the expression because it could produce some arbitrary thing. Now, admittedly, it can look syntactically inside of it, but if it's just some variable that refers to some other expression, it's completely stuck. But that's not the case with type class metaprogramming. Because in type class metaprogramming, even if we have some definition of something that's defined in some other module, and then we apply a function to it, then it can still know, I know what the type of that x is, and therefore I can perform a transformation. And if we inline that definition, which we can do because Haskell's pure, then we can basically say, oh, it turns out that we're not even done because there's another use of show in there, and then we can continue using the type information to continue this elaboration process. And so again, we get this kind of recursive feedback loop that I was talking about earlier, where we're performing code generation despite the fact that we don't have a direct means of expressing that. It's kind of an indirect way of expressing that. So macros are really, really good at local transformations. They can provide custom syntax. They can add new features to a language. You can't do that with type classes because you're constrained to the value language of the value language of the language. You can't extend that. You can't extend the expression structure of the language. But they do allow you to perform semi-global transformations where it can essentially the type system is performing an analysis of your program that is transmitting a lot of really interesting, rich data through your program. And wouldn't it be great if, as metaprogrammers, we could have access to that super rich world of data that we normally don't have access to when we're using macros in a dynamically typed language? So we would like to be able to have both. We would like to be able to have our cake and eat it too, and essentially allow our macros to have access to this rich world of information that Haskell metaprogramming has. Because again, with that server example that I was talking about earlier, you can't easily express that precisely with macros in a dynamically typed programming language because you don't have the link between what type is this thing, what is it, how do I serialize it, maybe you can do some kind of dynamic dispatch, but if you're going the other way where you convert strings to your data type, you can't dispatch on strings because you need to know what the data type is. You need that information from the type system. So we already have macros that take code to code. Can we get macros that take code plus some type information to code? So this type information could be maybe the type of some sub-expression passed to the macro. It could be the expected type that the macro is expected to expand into. So the answer is yes, we can. And indeed, Hackett makes an attempt towards doing this. But there are some caveats. So I want to say that up until this point, essentially everything that I've talked about exists in Hackett proper today, in the sort of experimental work-in-progress implementation that exists. This is sort of the forward-thinking aspirational goals of Hackett. And I'm going to show you a couple examples where we can do this today. And then I'm going to show you a couple of examples where there are some problems and why. So first of all, here's an implementation of something that I didn't really come up with this. This is thanks to David Christensen, who submitted a pull request and implemented this idea. But essentially, this is an implementation of typed holes. So it's where we can say, I have a part of a program that I don't want to write yet, but I want the compiler to tell me what its type is. And so this is actually implemented as a macro, this to-do thing. So how does that work? Well, we have a macro definition. And this is not a particularly long macro, but again, if you're not familiar with Hackett, most of it doesn't make any sense. That's OK. The second line says make expected type transformer. And what this essentially does is it says, I want you to tell me, I want the compiler to tell me what the expected type of this expression is. And then I promise to expand into some particular type. Or I promise to expand into an expression of that type. And if it doesn't, then that's a type error, and we complain and we blame the macro. But otherwise, it's able to do anything that it wants with that additional information. And this is OK because we've restricted what the macro is allowed to do a little bit. It's not allowed to arbitrarily get type information. It's able to get some. Another example is instantiation, explicit instantiation. Again, this is something that had to be baked into the compiler in Haskell. It was relatively recently added to the compiler, visible type application. Admittedly, this doesn't go quite that far. It's not quite as fancy. But it does allow us to explicitly instantiate particular types or particular values at particular types. And again, this can be implemented as a macro. Now, this looks like kind of a scary macro. Most of it's error reporting. But essentially, what's happening is at the top of this, it's saying, tell me the type of my sub-expression. And then I'm going to expand to some other sub-expression that uses information about the type of that sub-expression. So this is something that's, so the next two examples I'm going to give you are not currently possible to implement in Hackett. But I think that theoretically it is possible. Just have to figure out exactly how to do it. But I want to give you some examples of what they are and why it's hard. So in this particular example, maybe we want to generate a catamorphism. Now, if you're not familiar with what a catamorphism is, that's OK. Turns out I'm not really either. But it's kind of like a fold. So we can basically say, for example, on lists, it's just fold. Right? We can say, given 0 and some accumulation function, then we can accumulate all the elements. On either types or optionals, then we're saying, here's something for the left case and here's something for the right case. And this is really mechanical. It's really easy to write these functions. It's just like case analysis functions where you just give functions in place of the different cases of the case analysis. And it's completely mechanical to implement this. The problem is that because Haskell has global type inference, in order to figure out what the type of the expression is to give to the macro, it might need to know what the type of the expansion is. And so we have this loop, right? And so essentially, we always have to restrict what the macro has to make some promise that says, I'm going to expand into something like this. And then later, we have to make sure that it obeyed that promise. And so this is kind of hard. Maybe we can figure out a way to do it eventually. I don't know. Another example is we could build really fancy sort of DSLs where this is a SQL DSL where in order to figure out what variables to bind, we need to know what the expected type is, because this will produce some record. And based on the expected type, we know what table we're querying, and then we can bind some variables. This could be a terrible idea. It could very well be a terrible idea. But it's something that we could theoretically do with type information. So how do we do this? How do we actually implement this? Why is it that existing attempts to add macros to Haskell have not done this? Because there actually have been a few. So if we look at a compiler, the way that it works is essentially we have the input program, we parse it, we send it off to the compiler, it runs an optimizer, maybe something happens, it spits out bytecode, right? A really, really simplified version of a compiler. So if we want to add macros to the compiler, all we do is we add an intermediary step. We say, take the program, parse it, expand the macros, compile it. And the same thing is true for type checking, right? We parse the program, we make sure the types are correct, then we compile the program. So a naive combination of these two things just basically says, let's put the macro expander in front of the type checker. We'll expand all the macros, and then we'll check that the fully expanded program is correct. And if it is, then that's great, and we'll compile it. And if it isn't, then we raise a type error. But there's problems with this. There's problems with this because, one, it means that once we get type errors in terms of this fully expanded program, which may not have any real relationship to the user's original program. But the bigger issue is that the type checker runs after all the macros have gone away. So macros cannot have access to type information. It's just impossible. The type information isn't there yet. So in fact, Racket has an existing statically typed language in the distribution, typed Racket, and it uses this technique. And it's still a good language. It's a gradually typed version of Racket, because essentially what it's trying to do is type check idiomatic Racket. And it's still pretty impressive because it manages to embed the entire type checker into Racket, but it does not allow Racket macros to access type information. So figuring out how to do this actually required a significant step forward, which I cannot, I traditionally call this list-flavored Haskell. I don't want to have list-flavored Haskell. I want to have a deeper embedding than that. So in order to figure out how to do this better, we had to make a significant step forward. And I did not come up with that. I cannot take credit for that. But essentially, the idea is that we parse the program, and then we interleave expansion and type checking. And doing this is really subtle. It's really difficult. If we do it, then we can get something that is much more than just a list-flavored Haskell. We can get something that's fundamentally transformative, that we can actually have new abstraction tools. And the information about exactly how to do this comes from a Popple 2017 paper. I had nothing to do with it. It's a fantastic paper. If you're interested in figuring out exactly how this works, take a look at that paper. It's pretty readable, although that comes from me as a perspective of, like, I'm a Racket programmer. Maybe it's not so readable if you're not a Racket programmer, but you can give it a look. So by doing this, we can have something that's significantly more capable than just let's bolt a macro system onto Haskell. And Hackett does have to extend this type system as macro system considerably to build a constraint solver and non-local type inference, but it does work. So that's a lot of information. But to recap, Hackett is a Haskell that's been extended with macros. This gives us a lot of things that programmers actually want. It gives us the ability to extend the language. It gives us the ability to write better DSLs, things that we wouldn't be able to do necessarily in Racket or in Haskell. Macros augment existing models of Haskell metaprogramming. So they sort of complement each other. They overlap in some ways, but I think for the most part, if you're really using these things well, you can use them for sort of orthogonal purposes and play to each other's strengths. We can perform limited forms of type-directed macros. We've demonstrated that we can do useful things with them. We've been able to implement 2 GHC extensions as macros rather than baked into the compiler. Hopefully we can do more of that in the future, but again, that's much more experimental. So that's it. That's all I have to say. It was a little shorter than I expected it to be. Maybe I went through it a little too fast. But if you have any questions, please ask.
Next question?
Should I be afraid?
No, you should not. That was a lovely talk. Thank you. It's really, really good. I even understood most of it. So one of the things you described was that the difficulty getting type errors in terms of the expansion of the macro. So one way which you might try to address that be to say, maybe we could write, in Haskell you can write a type signature for a function, and then you should be able to type check calls of that function without looking at the implementation of the function. That's what type signatures do. So the question would be, I'm pretty sure you have somewhere something that's equivalent to a type signature for a macro. And I've often wondered about, the place I get snookered every time when I think about that is, how would I do that for a macro that introduced variable bindings, that is, that took patterns as arguments? Yeah. So how do you do that? That seems miraculous.
That's a really good question. The answer to that is we don't. And actually, this is something that I think that would be really wonderful to have, and I was actually talking to somebody about this relatively recently, just a couple weeks ago, which is that we can describe the types, we can describe signatures of values totally separately from their implementations, and that's wonderful. That allows us to have first-class modules, for example, and nice module systems. But we don't know how to do that with macros. We have no idea how to do that with macros. And we still don't have any idea how to do that with macros. There's people that are doing interesting research into that area, trying to give types to macros. Currently, I haven't been trying to do that. But it would be something that I would love to explore in the future. There is kind of the question of then how do we do this correlation that you're talking about. I actually have a couple extra slides for that. So, so it turns out that, and this is something that I think a lot of the time macro systems get a pretty bad reputation, and I think that that reputation is actually completely warranted. Most macro systems that I've used have been atrocious, and the error messages have been terrible, and things go wrong, and it's impossible to debug. So the reason for this is, as I was kind of saying, we have a source program, it has macros in it, we expand some of the macros, we expand some more macros, and then eventually we get a final program. A type or a runtime error happens right there. How do we know that we really want to report it right there in the original source program? This is hard. So there's actually a lot of ways that macros can go wrong. It's not just runtime errors, it's not just type errors. So there are things like errors in expanded code, macros that were used incorrectly, like here somebody used let instead of putting an identifier there, they put a number. And there's also sort of the hygiene problem, right? Name conflicts. And there's actually a lot more of these. But the good news is that because these are problems that existed, Hackett, the host language that I'm implementing this in, has solved the, well, not solved, but it's made these problems a lot better. And so Hackett's able to take advantage of existing machinery for source location tracking, where it's able to know, OK, this expression came from here in the original program, and therefore I can report a type error in terms of that. And it has to do a little bit of bookkeeping itself. It's not completely automatic, but it's pretty good. And that's how, like in that original program, when I said, you know, in the macro, I can change the type. I can change the integer to a string, and it was still able to pinpoint where that was. And it's able to do that even though there's all these transformations happening. So again, most macro systems don't do this. If you use like Clojure or common list macro system, they don't do this. You can get really useless error messages. But Hackett's macro system, for a while now, has been able to solve this problem.
More questions?
Yeah, I was wondering, why did you need to add the parentheses to the syntax? Because I was thinking like you would just need a new keyword to define a macro or something like that.
That's a really good question. I almost had an additional slide for that, but unfortunately I didn't put it in the slide deck, which would have been really amazing. But essentially, you know how I said that macros are functions from AST to AST. If you've looked at the actual Haskell AST, it is very complicated. It's very complex. And the reason for that is because every single type of expression, every single permutation has a different case. So like the definition of the expression data type is 126 lines long. I know that because I almost put this in the slide. But working with that sort of thing would just be too unwieldy for macro writers. And it doesn't, it's too coupled to the concrete syntax of Haskell. Whereas when we use S expressions, like the things that are just, if I go back to here, right, like this is just built out of ordinary data structures in the programming language. It's lists and identifiers are basically just strings, and literal data are just the literal data. And so rather than being like a function call, it's just essentially the much closer to what the user actually typed. And so we're able to write functions on these without being as coupled to the specific forms that are built into the language. And that's why S expressions are good for writing macros. If people say homoiconicity is like a thing that's specific to Lisps, they're lying. You can have any language is homoiconic with its AST. The advantage of Lisps is that the AST is really simple.
More questions?
Okay, so Hackett is a merge, some sort of merge of Hackett and Haskell, but you started from Hackett going to the Haskell. Do you envision being able to do that from the other way around? Starting from Haskell and moving to the Hackett side of things?
So the simple answer to that question is no, and I can explain why. Essentially, I was able to reuse the Hackett macro system because I embedded the Haskell type system in the Hackett macro system. And because the Hackett macro system is just, you can do arbitrary code, right? It's Hackett functions. Then that's possible to do. It's string complete. you cannot embed a macro system in the Haskell type system because it does not provide the capabilities. And reusing the GHC type checker would be difficult because it makes assumptions that Hackett does things subtly different than what GHC does in a couple of different places to enable macros. It doesn't have some features, like implementing certain features of Haskell in a macro-enabled language is probably significantly harder than what it already does. So this is a stripped down set. It's not just standard Haskell. It has some additional extensions like functional dependencies, multi-parameter type classes, higher rank polymorphism. But it doesn't have type families. And those, I think, things like that would be very difficult to just reuse. So the other thing to add is that Racket is really designed for building languages like this. I talked mostly as if Racket were a programming language, but that's not really true. It's actually a system for making programming languages, and there just happens to be a programming language in that system called Racket, which is confusing. But in that sense, like when I actually showed the demonstration of this hashlang Hackett at the top is essentially saying that this program is written in Hackett, and a hashlang Racket program would be using the Racket programming language. So, and all this like fancy type tooltip stuff that I have, this was really easy to add because Racket is designed for this sort of thing. I can right-click on this and I can say view documentation. I didn't have to build an IDE to do this, right? I mostly got it for free. Implementing all of that stuff is significantly more work, and even just implementing a macro system is pretty hard. So at least one that does all the things that are necessary for building something like this.
We still have time.
So interestingly enough, I've myself been working on a web server with dependent types, which has a striking similarity in syntax to what you have. And what I found in my development is that dependent type really allowed you change the development cycle very, very nicely. So for example, you put your the type definition for your server, and then you ask the compiler what should the implementation be like, and then it will evaluate at the type level and returns you the type value and say, oh, we should like have from string to string, and then this is a point, for example.
Sure.
Have you found like some similar differences from developing in Haskell to developing in Hackett, where the development cycle is different, sometimes better, sometimes worse?
Yeah, I mean, I think it's hard to compare them directly because one, Hackett is very young, and the things, like it has a bunch of type system features. It has almost no standard library, which means building actual programs. I mean, that's, right now, I think it's gotten to the point where like I was implementing all these type system features. Now I really need a better library. I need a better compiler to actually make it efficient. But, so in that sense, I don't have big programs to compare directly, which hopefully I will relatively soon. But I think that like simple things that have been different are in situations where even there are a couple people that I know who have been experimenting with the language who have just said like, oh, originally I didn't have special syntax for lists. I had intended to add it at some point. But people were able to just say like, here's a macro that adds special syntax for lists. And it even works in pattern matching forms because pattern matching is extensible. So maybe the best example I can show is it's not transformative in the sense of writing programs yet because I haven't written that many programs. But I have been able to actually get a number of contributors to the language because of the fact that it's modular and it's implemented as this tower of macros. People can just add like one little piece of the language without having to understand the whole compiler. And that's pretty cool. Obviously, that's true to a lesser extent in GHC, which is fairly modular, but the dividing line here is pretty explicit, which is cool.
I think one more quick question. Simon?
If it's still available. So you probably have a slide about this, mutter, 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 template Haskell?
I don't have a slide about that.
You don't?
But it's a good question. I'm actually glad you asked it because I probably should have included it in the talk. But template Haskell, so I will say GHC has like a lot of different metaprogramming systems. Template Haskell is one of many. It has GHC generics, template Haskell. One of the advantages of Hackett is that we can subsume some of those because they overlap in confusing ways. But template Haskell is not a macro system. I mean, maybe it is by some definition. But from a Lisp programmer's point of view, it's not a macro system. It's a splice system. So what's the difference? Well, with a macro system, it's code to code. With a splice system, it's you have a function that takes ordinary Haskell values and produces code. So what I mean by that is that you couldn't implement, say, this section thing in template Haskell. You could use quasi-quoters. You could call into the Haskell parser, which you can't do currently, but you could use one of the open source ones. And you could try to use a quasi-quoter to like parse a string. But that would be pretty awkward. You can't do this in template Haskell because it's a binding form. You can't implement new binding forms with template Haskell splices. So there's some ways in which they overlap, but I would say in general they don't. The other thing about template Haskell is that there are things about template Haskell assumptions it makes that Hackett doesn't make. So like template Haskell says, if you have a top-level splice, we'll have to divide the whole program into 2 pieces and then type check them independently. Hackett doesn't have to do that because it does clever things with expanding things partially and then going back and doing other things and then coming back, which the macro system already does. So it was easy to take advantage of some of those things.
So our time is up. Let's thank Alexis again.